So now we're on section 8.1 homework help. Normally I would have the answers turned off for some of the more basic exercises at the beginning, but I want to emphasize some ideas here. And so I want you to look at this right here. Remember, now again, this won't make any sense unless you've watched the lecture video. If you're trying to do this just by watching the homework video, it won't make much sense to you. So please go back and watch the lecture video and read the section as well before you begin this homework. So we're going to have two different populations. The original population, sometimes referred to as the parent population, and its mean is symbolized by mu. Then you have a new population of all possible x bars, and its population consists of all possible x bars, and its mean, mu of the x bars, is the same value always as the mean of the parent population. So again, two populations. The original population symbolized with its mean symbolized by mu, and the new population of all possible x bars, whose mean, the mean of all possible x bars, symbolized by mu subscripted x bar, those will always be the same value. That's super important. Now, again, two populations. The original population has standard deviation sigma, and the new population of all possible x bars has standard deviation sigma subscripted x bar. Even though the means will always be the same value, the standard deviations will always be different given by this formula. Do you see how this square root of n is in the denominator? As n gets larger, all right, it keeps dividing into the original number, making the new distribution standard deviation smaller, all right, which makes the new distribution tighter, always a tighter distribution. The standard deviation of the sampling distribution of all x bars, denoted by sigma x bar, is also called synonymously the standard error of the mean. Is the statement above true or false? The distribution of the sample means will be normally distributed if the sample is obtained from a population that's normally distributed regardless of the sample size. That's true. What you have to remember, and again, go back to the lecture, whenever you're dealing with the distribution of the sample means, the x bars, you have an either or requirement. Either the original parent population has to be normally distributed, or you need a sample size greater or equal to 30 for this new distribution of the x bars to be normally distributed. Again, two populations, the original population of individual scores and a new population of all possible x bars. This new population will be normally distributed if the parent population is normal, regardless of sample size. That's this question here. Or if you haven't been given the information that the parent population is normally distributed, you need to have a sample size greater or equal to 30 for this new distribution of x bars to be normally distributed. This is a little bit of a trick question, but it'll go back to this right here. See where it says to cut the standard error of the mean in half, the sample size must be doubled. That's false. All right. The sample size must be increased by a factor of 4 to cut the standard error in half. Why is that true? Let's go back a little bit. What you're dealing with, this is the standard error right here on the left. All right. And in order to cut that in half, you need to have a 4 times the original sample size, 4 times n, because when you take the square root, a 2 will come off, 2 will come out, it will be in the denominator, and that'll form your 1/2. And so to cut the standard error of the mean, which is the sigma of x bar, in half, you need to put a 4 here in front of the original sample size. So you have to increase the original sample by a factor of 4. If you want to cut this in terms of make it 1/3 as large, then you need a 9 here to get a 1/3 coming out. If you want to make it 1/10 as small, you would need 100 times n. Okay, think about that. It's mathematical. So now we have a simple random sample of 57. Because that's greater or equal to 30, we don't care what the parent population looks like. The new distribution of the x bars is going to be normally distributed no matter what. So what is the sampling distribution of the x bars? Well, it's going to be normally distributed, right, because the sample size is sufficiently large. its mean is going to be the same as the original mean, the 74, but notice that the standard deviation is not 8, it's been reduced. How has it been reduced? This value right here will be sigma 8 divided by the square root of n. Sigma divided by the square root of n. That's super important. Mu of the x bars is mean of the parent population, but sigma of the x bars is the original parent population standard deviation divided by the square root of the sample size. Determine x bar and sigma x bar given the parameters. This is the same story. Mu of the x bars is always the same as the parent populations, but this right here will be the original sigma divided by the square root of n. Here the square root of n is 7. 7 divided by 7 is 1. So look at this right here. Now my question to you is, do you understand that this is a picture of the distribution of the x bars? It's so important that you notice that. It's a sampling distribution, meaning it's the new distribution of all possible x bars. The mean of that is 500 right there at the center. Now, what is the value of sigma of x bars? Where did that 20 come from? Okay. Well, remember that with a normal distribution, the inflection point, concave down, concave up, the inflection point occurs at one standard deviation above the mean and one standard deviation below, and because that's 20 units over to that inflection point, that standard deviation must be 20. Now, do you see how the distribution of the x bars is normal? Remember, we have two conditions. Either the parent population is normal to begin with, or we have a sample size that's greater or equal to 30. Here, if we already have a normal distribution for the x bars, when the sample size is less than 30, then the parent population must be normal. Okay. Now, they want you to compute sigma, the standard deviation of the parent population. So what you're going to have to do, look at this. Your numbers will be different, but this value is 20, n is 16, so we go back to this formula right here, and over here on the left I put in 20. All right, over here on the left I put in 20. I leave this as a variable unknown, that's what I'm trying to solve for, and here I put in the square root of the sample size. In this particular case, the sample size is 16, so the square root of 16 will be 4, multiply both sides by 4, and I'll get the new standard deviations 80. See, all right, your numbers will probably be different, but it's the same idea. So, describe a simple random sample of size n equals 81. Suppose a simple random sample of size n equals 81 is obtained from a population of mu equals 74 and sigma is 9. Again, these numbers are from the parent population, but now we're talking about the new population of all x bars. Okay, so let's go back to this. Mu of the x bars will be the same mu as the parent population, but sigma of the x bars is going to be sigma of the parent population divided by the square root of n. It's so important that you remember that. So here they're going to ask us to do a normal distribution. Okay. So go to StatCrunch. This is just like chapter 7, by the way. Calculators, normal. And they want me to have, well, let's see what we got going on. Mu equals 79. Yeah, right, 74. Now, the standard deviation will not be 9. What it is, it's 9 divided by the square root, SQRT. Okay, and the sample size is 81. This is an easy one. I could have just done it in my head. All right, because the square root of 81 is 9. 9 divided by 9 is 1. But I just want you to see that process. So what you do is you put in the original standard deviation, backslash for divide, and then SQRT for square root, and then put in the sample size, and then do what they're doing here. Now, something that's very different, and you might have learned this in chapter 7, but when we were working with discrete random variables in chapter 6, it was important to distinguish between greater than and greater than or equal, less than and less than or equal, but for continuous random variable, greater than and greater than or equal, less than and less than or equal are exactly the same things. And so we only have two choices here. just greater than or equal to and less than or equal to. So if it's greater than, choose greater than or equal. If it's less than, choose less than or equal. So we want greater than, right? See that? And they want 75.65 there. And I compute, okay, and I get my answer. Do you see it right there? You do the other ones just the same. For this bottom one, you use between. Okay, let's go to the next. So suppose a sample, random sample of n is 10 is obtained from a population mu equals 69, sigma is 18. What must be true of the parent population? Well, because our sample size is small, the parent population has to be normal. So this new distribution will be normal, okay, if the parent population is normal. It'll have mu the same as the parent populations, but sigma is not 18. It's 18 divided by the square root of 10. How do I do this here? Same as what we were doing. You go back and use the normal calculator. So for the mean, I put in 69. For the standard deviation, I put in 18 divided by SQRT. And what's the sample size? 10. And what do I want? Less than or equal to, so I'm fine with that. I put in my 72.1, close parentheses, compute. Do you see how I have the answer? Okay, so let's go to the next problem. This is done exactly the same way, right? I'm on problem 11. Now this is different. Slow down on this and be careful. Do you see that we're looking at pregnancies? We're told that the parent population of all possible pregnancies has a normal distribution. So the parent population is normally distributed. The mean for that parent population is given by 193 in this case, sigma 13. But in part A, they want you to not use the central limit theorem. You're looking at an individual pregnancy, not a sample, an individual pregnancy. So when you do this on the normal calculator, all right, you want less than 189, but you're going to use mu equals 193 and sigma equals just 13. Do not divide it by the square root of n because you're talking about an individual pregnancy. It's an important distinction. In part B, they want you to redo it, but with a sample of 19 pregnancies. So when you do it, okay, you're going to use the same 189, but you're going to use mu 193. Now sigma is going to be different. It's going to be 13 divided by the square root of 19. 13 divided by the square root of 19. And you get a lower probability. See 9% here, 37% up here. It's because when you reduce the standard deviation, this new distribution of x bars is going to be much tighter, and the scores bunch up around the center more, and so it's more difficult to get scores away from the mean. Okay. The purpose of this exercise is to show as you increase sample size, the probability of getting a score very far away from the mean diminishes. Right? As you increase sample size, your new distribution of x bars gets tighter and tighter, and almost all the scores are bunching up around the middle, the mean. And it's very difficult to get scores away from the mean as you increase sample size and you look at the distribution of x bars. So in this problem down here, what is the probability that a random sample of size 20 will have a mean gestation period within 8 days of the mean? Within 8 days means plus or minus 8. Okay, and so what you have to do is use between on the normal calculator. You go up here to 193. 185 is 8 less than mu. Okay, 185 is 8 less than 193, and 201. And so you're looking at the probability of getting, in this specific case, a score between 185 and 201. So this problem is also very similar to the last problem, but in part A, it's a randomly selected student. So you're going to use a normal calculator. All right. You're going to use mu of 92 and sigma of 10. Then for part B, you're looking at a sample and you want to know what's the probability of getting an x bar. That's more than 97. Notice it's the same number, conceptually just like the last problem, but now your standard deviation is going to be modified and it's going to be 10 divided by the square root of 12. As you increase sample size, the probability of this occurring diminishes for the same reasons I explained in the last problem. And here, you're going to use the square root of 24 in the denominator when you calculate the standard deviation for the x bars. So down here, in this last problem, a teacher instituted a new reading program at the school. After 10 weeks in the program, it was found that the mean reading speed of a sample of 22 students was 94.4. What might you conclude? What you should do in this part of the problem is implicit, so I'm going to explain it to you explicitly. The mean is 92. You instituted a new program. You want to know, is that new program working? Meaning, what's the odds, all right, of getting this 94.4 if it's true that the mean is 92? So what you have to calculate, the probability that x bar is greater or equal to 94.4. The probability of getting a sample mean this far ahead of what you expected, the 92, all right, greater or equal, this extreme or more so. And so for the mean, you're going to type in 92. For the standard deviation, you're going to use 10 divided by the square root of 22, okay, and compute the probability that x bar is greater or equal to 94.4. The shape of the the distribution for this parent population is unknown. You see that? Unknown. And so that means we need a sample size greater or equal to 30. What's the probability of the random sample n equals 45 results in a sample mean less than 20? Use the normal calculator, all right? Use a mean of 21.3 and use a standard deviation of 4.8 divided by the square root of 45. Now, suppose the manager agrees to pay a bonus of $50 if they meet a certain goal. On a typical Saturday, the oil change facility will perform 45 oil changes between 10 a.m. and 12 p.m. That's our sample size. Treating this as a random sample, at what mean oil change time will there be a 10% of it being at or below? And so at or below is less than. All right, leave that blank, but set this to 10%, 0.1. Okay. And standard deviation is, well, 21.3 for the mean, 21.3. And standard deviation will be 4.8 divided by SQRT, 45. Close that. Now I'm computing the cutoff. See, I left that blank, but I put it in the area. And the cutoff is 20.38. Rounded to one decimal place, 20.4. What they're asking me to do is less than or equal, okay, put in the mean, put in the standard deviation, and set the area, set the probability to 10%. Okay, hit compute, and it gives me the value.